Capacitors. Capacitors store charge and therefore energy. Conceptually, the capacitor can be thought of as two metal parallel plates. We've seen this in our unit on electrostatics. If we place positive charges on one plate and negative charges on the other, an electric field will be generated between those two plates, parallel and uniform field lines. How do we get those charges onto the plates? We connect the metal plates to a battery. Imagine we start with empty parallel plates. When I close the switch, positive charges flow out of the battery and go onto the plate. The first charge goes on really easy because there's no positives on the plate to repel the incoming positive charge. That positive charge will now repel a positive charge from the opposite plate, sending it to the battery. As that positive charge leaves the neutral plate, that plate will now become negative. A weak electric field appears between the plates. The next charge comes out of the battery and approaches the positive plate. But there's already a positive charge on the plate now, so the second charge is a little harder to get on there. Another positive is repelled off of the negative plate, making the negative plate more negative. And the electric field starts to build up. As this process continues, it's going to take longer to get additional charges on this plate because there's already charges there. Eventually, the charges build up to the point where no more charges can go onto the capacitor. There'll be a voltage gain here, followed by a voltage drop across the capacitor. When this voltage over here is equal to the voltage over here, then the current stops flowing and we say the capacitor is filled. We can make a graph of charge on the plates versus the voltage across the plates of the capacitor. When there's no charge on the plates, we have no voltage. As the voltage across the plates builds up, that's because there's more charge. And the relationship is linear. More charge on the plates creates more electric field, which makes more voltage. The slope of this line is charge over voltage, which is what we call capacitance. Capacitance is exactly like what this word sounds like. It has the capacity to store charge. And of course, the more voltage you have on there, the more charge you can store. That ratio is constant as we increase the voltage. Capacitance is measured in coulombs per volt, which is equal to a farad. The area under this curve has a special meaning too. It's charge times volts. Well, if voltage is work per charge, when we multiply by charge, we get work, or the potential energy. But the area is the shape of a triangle, so we need to put a 1/2 out in front. So these are the two formulas we need to use when dealing with capacitors. Let's set up a problem to see what's going on. We have a capacitor of 0.4 farads connected in series with a 20 ohm resistor and a 6-volt battery. When I close the switch, what will be the initial current? The current will flow into the capacitor. The capacitor does not have any charge on it yet, and therefore will not oppose any new charges coming in. There's no voltage drop across that capacitor. The charges that come in just come right out the other side and then go through the resistor. The full voltage drop will occur on the resistor, and we can find the current by using Ohm's law. We get an initial current of 0.3 amps. Now, after a little while, charges will start to build up on the capacitor. Because these charges are there, there will be a voltage drop across the capacitor. Well, let's just say the capacitor is not full yet. So we'll just say we have a voltage drop of 1.5 volts. In this situation, what do you think the voltage drop will be across the resistor? It has to be the rest of the voltage. What will be the current through the circuit at this point? Again, we can use Ohm's law. The current is now down to 0.225 amps. And we can see as the capacitor starts to fill, the current is dropping. And now more charge has appeared on the capacitor. We have a voltage drop of 3 volts on the capacitor. 3 volts, therefore, will be the drop on the resistor. And the current is cut in half now. Continuing with this trend, as the voltage builds up on the capacitor, there will be less voltage drop across the resistor. Well, eventually, we're going to have the entire voltage drop across the capacitor. And there'll be no voltage drop across the resistor. The current will be 0. The charges that are trying to flow onto the capacitor are being pushed on with a force that is equal to the repelling force of the charges that are already there, and nothing can flow. The capacitor is filled. Now let's think how long this is going to take to happen. We'll draw a different graph to analyze this. This is charge per time, not charge per volt. How much charge will flow onto the capacitor initially? Look at the current. The current is big initially, so the most charge flows on in a short amount of time the moment we close the switch. There's nothing here to repel the incoming charges, so we build up charge quickly. And after a little while, it's a little harder for the charges to get on there because there's charges on there now. More charges, harder to get more on there. The current has reduced, which means less charge will flow on there in the same amount of time. And again, as more charges build up, it's harder to get more charges on there, so less charge will flow on in the same amount of time. Eventually, the capacitor is filled, and no more charge will flow on at all. So what does the curve look like? It's going to rise quickly and then level off. Drawing a tangent line at time 0 tells us something about the current. The slope of this line is charge per time. That's the current. And if it's at time 0, it's the initial current. What's the slope after a long time? If no more charge is flowing on, then the slope is 0, and that's the current. Current is 0. This all agrees with the lab with the capacitor and the light bulb. When we closed the switch, the light bulb was bright because the current was highest. Eventually, the light bulb got dimmer, the current was less. And eventually, the bulb went out, and after a long while, the capacitor would be filled, and there would be no more current in the circuit. Well, to summarize, if we close the switch, the capacitor is empty, the charge rises quickly, and then levels off. If we take a look at the current versus time graph, the current starts out high and drops off, which agrees with the slope of the charge graph. Now, in theory, it's going to take an infinite amount of time for this current to come to a stop. As the voltage builds up on the capacitor, it takes a longer and longer amount of time to get another increment of charge on that capacitor. So this is really an exponential decay graph. Okay, so let's go back to the original setup, close the switch, and charge up the capacitor. After a while, the capacitor is fully charged. There's no more current flowing through. How can I show that the charges are actually stored in that capacitor? I'm going to remove the battery. Now, when I close the switch, the positive charges will repel each other and flow off of the left plate and go clockwise. Those positive charges will flow through the resistor and recombine with the negative charges on the right plate. What do you think the graph of charge versus time on that capacitor will look like now? At time 0, the capacitor is fully charged. The voltage across the capacitor will be at the greatest. Therefore, the voltage across the resistor will be the greatest. Whatever voltage gain we have on this capacitor will be the voltage lost across the resistor. The current will be the greatest. The charges are repelling the greatest. There's the most of them are in there. They want to get out. That's going to give you the greatest current, which means you're going to lose the most charge in the beginning. As the charge flows out, the voltage drop on the capacitor is reduced. Therefore, the voltage across the resistor is reduced, and the current will be less. You will not lose as much charge in the same amount of time. And the process continues. To lose a certain amount of charge, it will now take longer and longer because there's less voltage on the capacitor. Well, what will the graph of current versus time look like? Think of current as the slope of the charge graph. But now the slope is negative. Why is this negative current? Because if charging the capacitor is positive current, discharging the capacitor, the current is now going the other way. We call it negative current. And it agrees with the charge versus time graph. And the current tapers off as well. Okay, let's try a discharging problem. We've got a capacitor of 0.25 farads. We charged it up previously with a 9-volt battery, and now we're about to throw the switch and connect it to a 10-ohm resistor. What will be the initial current? The capacitor is providing 9 volts across the resistor. The initial current is 0.9 amps. Now let's find out the amount of charge that's stored on that capacitor. We know the formula, capacitance is charge per volt. 9 volts is the voltage on the capacitor, and we can calculate Q. And we get 2.25 coulombs. Now we can also ask ourselves how much energy was stored in that capacitor. We'll use the formula potential energy equals 1/2 Q times V. And we get about 10.1 joules. We're going to close the switch and current will flow. Positive charges will come off the capacitor and the voltage will start to drop on that capacitor. Let's say we get down to 6 volts. What's the story now? The voltage across the resistor is 6 volts. What's the current? 0.6 amps. How much charge is on the capacitor? And we take the capacitance times the voltage, and we get 1.5 coulombs. What's the energy stored in the capacitor at this point? We use the potential energy formula, and we get 4.5 joules. All these numbers agree with the initial values. We have 0.9 amps to start with, and we're down to 0.6 amps. We had 2.25 coulombs of charge stored on the capacitor, and now we're down to 1.5 coulombs. And the initial potential energy of the capacitor has now dropped to 4.5 joules of energy on the capacitor. So the question now is, how much energy was dissipated by that resistor? We're talking about waste heat. We had a certain amount of initial energy in the capacitor, and we went down to a final value. The energy had to go somewhere. It's not going into kinetic energy in circuits, we know that. So where'd it go? Waste heat. What are we going to do with all this knowledge? We should be able to do a capacitor lab. The first part should just be a demonstration that you can charge a capacitor through a bulb. Build the circuit, close the switch, and watch what happens. See if it agrees with what you expect. After you've waited a long while, discharge that capacitor through the bulb. Close the switch and see what the bulb does. See if it does what you expect it to do. Now that you got things working, you can go back to charging the capacitor again, but this time take measurements. When you close the switch, measure the voltage across the capacitor. Should the voltage increase or should the voltage decrease over time? You can repeat the experiment and measure the voltage across the light bulb. See if it matches what you expect. And then you can repeat it again and measure the current. You think the current will be high in the beginning and then taper off, or go the other way around? You can do the experiment and prove it to yourself. Now, every time you do the experiment, you have to make sure, whenever you repeat the experiment, you have to make sure that you take a wire and connect both sides of the capacitor so that it will be drained. You have to do this for a couple of minutes, let that thing drain all the way, and then you can go ahead and restart your experiment. And of course, you could go back and discharge the capacitor and use the voltmeter and the ammeter to measure the volts and the current. I'll post another video on how to set all this stuff up in the lab in case you're not sure.